Okay, so welcome everybody, and thank you for joining us for this new webinar. Following on from what we discussed last time, today we will present the essential type model of MISRA C 2012. This is Lavinia, CSR at BUGSENG, and our speaker is Roberto Bagnara, who, long story short, is CTO at BUGSENG, computer science professor at the University of Parma, member of the MISRA C working group and of the International Standardization Working Group of the C programming language. As usual, before we start, please note that you can write your questions in the Q&A section throughout the entire webinar, and then at the end we will read them and reply. Okay, then let's turn this over to Roberto.
Okay, so thank you for attending. This webinar is a follow-up of the previous webinar where we talked about implicit conversions in C. And so the plan this time is to reconnect to the previous webinar by means of the two examples we have used at the other time. And then I will introduce the MISRA C essential type system. First, I will explain the essential type model, and then I will explain how to infer the essential type. And there will be a little test, a completely anonymous test, to which you are welcome to participate, about inference of the essential type. Then I will go through the MISRA rules that are based on the essential type model, and then I will draw some conclusions. Okay, so if you remember, a couple of weeks ago, we have seen this slide. So the hidden enemy. Who is the hidden enemy? The hidden enemy is implicit conversion. So we have this example where we have an implementation of a freeze alarm, which is meant to protect your house with this code. And suppose that the minimum temperature in Celsius degree is 1. So the variable min temperature C is set to 1. And suppose that the successive temperature readings are 5, 3, 2, 1, -1, -2, -5, -7. And frozen pipes result and they may burst. And can you spot the hidden enemy? The hidden enemy is due to the fact that there is an implicit and thus hidden typecast, which the language will insert, whereby the temperature C variable will be converted to unsigned implicitly. Okay, so -1 will become a very large number, and the same for -2, -5, -7. And so freeze alarm will always return false for these readings, and so the device is not working. And the other examples we did in the previous webinar was the imaginary friend. So the imaginary friend is something that some programmer may believe are there, and they are not. The example was the following one. So John wants to take the average of two 32-bit signed integers. And of course, John knows that the sum of two 32-bit signed integers can be larger than what can be represented in 32 bits. And so he uses 64 bits to represent it. So the code is this one. You see that is storing the sum into a 64-bit variable. However, average of 2 billions and 2 billions, which should give 2 billions, gives 666 instead. So can you guess what and where is John imaginary friend? And it's here. So John thought that the addition would have been performed in 64 bits, whereas this is not true. These implicit casts, of course, are not present, are not in the language, and so the addition is performed in 32 bits. And if it gives an overflow, then converting to 64-bit to store it into variable sum, it's too late. The undefined behavior already happened. Okay. So as a solution to this problem, we today explore the MISRA C essential type system. So the MISRA C 2012 essential type model is a refinement over the arithmetic types defined by the C standard. And the arithmetic types are partitioned into so-called essential type categories. And the categories are as follows. There is the Boolean essential type category, which comprises underscore bool, available in C99 and later versions of the language, special type defs or enumerated values that have been defined by the user to represent booleans. So this is the only possibility in C90. Then there is the character essential type category, which comprises only plain char, so the type char without any specification of signedness. Then named enums have essential type category enum. Then the essential type category signed is used for signed char, short, int, long, and long. The unsigned essential type category is used for unsigned char, short, int, long, and long, all with unsigned in front of them. So unsigned short, unsigned int, unsigned long, and unsigned long. The floating essential type category comprises the types float, double, and long double. One thing to be noticed is that differently named enums are distinct, whereas all the anonymous enums are simply considered to be essentially signed constants. Okay, in anonymous enum, you use anonymous enums only as a way of declaring constants, and these are signed. Okay, so in MISRA C essential type model, two terms are used, wider and narrower, and they refer to the size of the C type. In the previous webinar, we have talked about the rank of a type. Okay, so the concept of wider and narrower has nothing to do with rank, even though there is a relation. But if long has the same size as int, then long is not wider than int, even though long and int have different rank. The rank of long is higher than the rank of int. But if they are not, they have the same number of bits, then neither is wider than the other. The MISRA C rules about essential types treat compound assign operators as if they were expanded, even though the semantics is not exactly the same. So, for example, A star equal B plus C is viewed as if it was A equals A times B plus C. Okay, so what is the basic idea behind the essential type model? Every expression that has an arithmetic type, as defined by the C standard, has an essential type category and a size. Category and size. The context of an expression that has an arithmetic type, the context has an expectation concerning the essential type category and size. When the expectation is not fulfilled, we have a MISRA C violation. Let's make the simplest possible example. As the guard of an if-then-else statement, the guard has the expectation of receiving a Boolean, something of essential category Boolean. If you give it something that has essential type category float, it's a violation. If you give it an integer, assign it, it's a violation. So in the if-then-else statement, in the context of the guard, something of essential type category Boolean is expected. And if you don't give a Boolean, then it will be a violation of some rule. Okay? So why is the essential type model there? It's to add further constraints to the C language, which is quite lax in this respect, so as to avoid some implementation-defined behaviors, to avoid mixing data that have a different nature, to improve code readability, to avoid C subtleties that we have explored in the previous webinar that, by the way, you can see in our YouTube channel. Subtleties that are related to the concept of promotion and the usual arithmetic conversion. As we have seen last time, they are quite tricky concepts. And in addition, such constraints that are imposed thanks to the essential type model use have the effect of improving code portability. Okay. So let us now talk about how we can infer the essential type of an expression. So the first thing to be understood is this: the essential type and the C standard types can be the same or they can be different. And the rule is this: when the C standard type is not int or unsigned, then the essential type is always the same as the C standard type. It's only when the C standard type is int or unsigned that the essential type may be different from the C standard type. So in the next slides, we will see situations where the C standard type is int or unsigned, and we will see what is the resulting essential type. So let's start. If we have defined spatially enumeration constants or integer macros for true and false, these are essentially Boolean. As I said, this is something you have to do if you are working in C90, where there is no built-in type bool. So you have to, say, construct your own Boolean type and Boolean constants. You can do this using enumeration or type defs or integer macros, and of course you will have to tell your tool about your choices. Anyway, all the things that you have defined to be essentially Boolean are of course essentially Boolean. A single character literal is essentially character, okay? So as type category character. Now let's move to constants and bit fields. In order to understand what is the essential type for a constant or a bit field, we need two auxiliary concepts. The first one is called STLR, the signed type with the lowest rank. It's the signed type with the size of the lowest ranks that can contain the constant or bit field. Okay, so as you can see, the essential type for a constant or for a bit field depends on the size of on the number of bits that are required basically to contain this constant or this bit field. Okay, so for example, STLR of 1, of the constant 1, despite the fact that 1 is a standard type int in C. Okay, so the constant 1 has a STLR signed character. Okay, so it's signed with the number of bits of the character type. Okay, UTLR is similar. It's the unsigned type with the size of the lowest rank that can contain the constant or bit field. So we'll see immediately examples. So the essential type of signed bit fields and signed integer constant is the related STLR. So let's take an example. 3, the constant 3 as type signed int. And similarly, for a bit field of size 2, declared size signed int df column 2, they both have standard type int, but the STLR is a signed character. So this is 8-bit signed on, for example, Intel architecture 32 bits, and it's 16-bit signed on the C2000, where both char and int are 16 bits. Okay, notice the difference. If I stick an L suffix to the 3, so I have 3L, this is standard type long. And as I said, the essential type can only be different from the standard type if the standard type is int or unsigned. So since 3L has standard type long, this is 32-bit signed on both Intel architecture 32 and on the C2000. Okay, notice this subtlety. The essential type of unsigned bit fields and unsigned integer constants is the related UTLR. So we can, of course, do very similar examples. You can do them by yourself. And the essential type of anonymous enum constants is the related STLR. As I said before, anonymous enum are seen just as containers for signed constants. Okay, now the behavior with respect to the operators. So the essential type of expressions, we see them for each expression. So for the comma operator, it's the essential type is the same as the right-hand operand. So this is easy because, as you know, the first operand is evaluated, but the value is ignored. So the relational, equality, and logical operators, they give rise to an essentially Boolean result. Okay, the shift operation, both the left shift and the right shift, only when the left-hand operand is essentially unsigned. If the result is an integer constant expression, so for example, if both the left-hand side and the right-hand side are constants, then you take the UTLR of the result. And otherwise, if they are not constant, if the result is not a constant at compile time, then the essential type is the same as the left-hand operand. So I have to explain why the restriction that this rule is only valid when the left-hand operand is essentially unsigned. So the philosophy behind MISRA C on this matter is as follows. If you play clean, then the essential type system will give you something. If you are not playing clean, for example, when you are shifting signed quantities, which is implementation defined, then MISRA C says you are on your own. So the essential type will be the same as the C standard type. So it makes no sense that we define this case. Okay, that's why the rule for the shift is only valid when the left-hand operand is essentially unsigned. If this is not the case, then the essential type will be the same as the C standard type. So you will have to look at the standard and see what is the result. For the bitwise complement, the same situation. The essential type is different from the C standard type only when the operand is essentially unsigned for the same reason. If it is signed, then the result is implementation defined because it depends on the representation of integers. And so this is why this restriction. And the rule is similar to the above one. If the result is an integer constant expression at compile time, then the essential type category is given by the UTLR of the result. And otherwise, it is the same as the operand. Okay? Unary plus, only when the operand is essentially signed or unsigned, the essential type category is the same as the operand. The unary minus, only when the operand is essentially signed, note this for a change, If it is the result is an integer constant expression, then you take the STLR of the result, and otherwise it is the same as the operand. For the conditional operator, the requirement is that the second and the third operands have the same essential type category, and then the essential type category of the result is the wider essential type between the second and the third argument. For the other binary operators, only when the operands are both essentially signed or unsigned, if the result is an integer constant expression, then the STLR or UTLR, according to the essential type of the operands, and otherwise you take the wider essential type between the operands. Okay, so again, this is only defined if you play cleanly. Okay, if you are adding signed with unsigned, this is not good. This is confusing, to say the least, and so you will have to take the essential type corresponding to the C standard type. There are special cases involving characters. So if you take an essentially character and you sum an essentially signed or unsigned, or the other way around, or if you subtract a signed or an unsigned from a character, then the result is essentially character. And why this? Because it is idiomatic to use addition of integers, for example, to convert lowercase characters to uppercase characters, okay? And the other way around. And similarly, if you take an essentially character and you compute the subtraction with another essentially character, then the result is essentially signed. Again, this is idiomatic use where you want to be, for example, independent from the character encoding, and you want to compute the difference in number of positions between lowercase a and uppercase a, for example. Okay, so it's time for a small test to see if you have grabbed the philosophy of the essential type model. So among the tests I could have chosen, I've chosen the most complex one. So usually understanding what is the essential type of an expression is trivial if you play cleanly. And so I've chosen all examples where, well, most of them, they do not play cleanly. So this makes understanding what is the essential type a bit more difficult. So as an introduction, we assume that we have an implementation with a 32-bit int and 64-bit long, and that we have the following declaration, which are very easy to remember. U8 is unsigned 8-bit. S16 is signed 16 bits. U16 is unsigned 16 bits. So let us start with the first poll, Lavinia.
Of course, I just launched it.
Okay. I'm not seeing it because
I'm not showing the results yet. If you want, I can show them.
No, I know.
Now it's still, yeah.
Now I see it.
Okay.
I see it. Okay. Okay. So as an observation, this expression is not very clean. You see that we are adding up an unsigned to a signed. So we are in the situation where the essential type model says you are on your own. So the essential type will be the same as the C standard type. Okay. So if results have stabilized, you can show the results.
Okay. There you go.
Okay. So you are showing the result now. Okay, so many seems to believe that the answer is 16-bit signed. No, the correct answer is 32-bit signed. So we have 14% of those who responded that are correct. So let me explain why. As I said, we are summing unsigned with signed, okay? Which is one of the cases where, let me go back, you see, only when the operands are both essentially signed or unsigned, okay, this rule applies. Otherwise, the result is the same as the C standard type. So U8 will be promoted to int 32-bit, S16 to int, sorry, the usual arithmetic conversions are such that the addition will take place in signed integer 32 bits, and this will also be the type of the result. Okay, let us go with the, let us continue with the next poll.
Okay. Here is the second one.
Okay, so here we have 10 plus 120. Which is well behaved in a way. So we are summing signed with signed, which is good. Another hint I can give you is that 10 plus 120 is a constant at compile time. Okay? So the essential type category will be the STLR of the result. Okay, time to show the results.
Can you see them?
I can see them.
Okay.
So the correct answer is 16-bit signed. Why is it 16-bit signed? Because 10 plus 120, they are both signed. It's a compile time constant, 130. On this machine, we have, so 130 doesn't fit into 8-bit. So it requires 16-bit. And this is why the essential type category is 16-bit signed. Okay, so let us continue with the next one.
There you go.
Okay, so notice that this is not well behaved. So we have signed plus unsigned. So the essential type will be the same as the C standard type. Okay, so you can now show the results.
Okay, should be able to see them now.
Yeah, so 10 plus 120u. So this gives rise that the 10 is converted to unsigned. So we have the addition of unsigned int plus unsigned int, and this gives an unsigned int, which on this machine is 32-bit unsigned. Okay. Remember that it is, in this case, it is the signed that is converted to the unsigned and not the other way around. So we have seen this example in the hidden enemy example. So let's continue with the next test.
Okay.
Here we have 10, which is signed int, plus 120L, which is signed long. Okay, so what do you think will happen? Yes. Okay, you can show the results. Most of you got it right. The result is 64-bit signed. Okay, because 120L as essential type signed int, 64 bits. Okay, and so as the rules say, the result as the same essential type category, so signed with the largest size. Let's go to the next poll.
Okay, there it is.
Okay, we have a single character literal, lowercase c, and we add 1. Yeah, very easy in this case. It is the exception that we have seen in the last couple of slides. So character plus an integer is a character. So let's see the answers. Yes, most of you agree. Character plus integer is a character. Okay. The last poll.
Okay.
Okay, here we have character plus character, which is not the exception. And we have seen that for the binary plus operator, the rule applies only if both operands have both essential category signed or essential category unsigned. Here we have that they have both essential category char. So the result will have the same essential type as the C standard type. Okay. No, many of you said character, whereas the correct answer is 32-bit signed. Okay. So as I said, these are basically the most complex example I could make. I don't know if it was a good strategy to do this. Maybe some of you now will think that the essential type model is not easy. Indeed, it is very easy if you play clean. Never mix signed with unsigned. Never mix data of different nature. Okay. So let us now go to the rules that are based on the essential type model. First rule, operands shall not be of an inappropriate essential type. This is a required rule, so you can deviate it, but it will require a formal deviation. Is decidable at the level of a single translation unit, and as all the rules we will see in this webinar, it applies to all the versions of the C standards. Okay, so what it means appropriate. There is a table, and here is the first part of the table. So when a cell like this contains a number, the number is an explanation saying why not. So, for example, you cannot address an array with a Boolean for reason in note 3. You cannot address it with a character. You cannot address it with a floating. Okay, this is a constant violation. Okay, whereas it is fine to address an operator with a none, with a signed, or with a non-signed. Okay, another example that we have seen, you cannot take the sum of two Booleans or two enumerated types. Okay. Let's see another example here. You cannot apply the logical operators to anything that is not a Boolean. You see that all the other cells in this row have a number, which means which is a pointer to the explanation of why not. You should see MISRA C 2012. I will go through the main reasons why these are forbidden in a second. Okay. Similarly, here we have seen the shift operators. You cannot, on the left-hand side, you cannot have a Boolean, you cannot have a character, you cannot have an enumeration, you cannot have a signed. I said that you cannot have a float. Okay. So you see, this table explains various things. For example, the first operand of the conditional expression, you can only have a Boolean. You cannot have any other thing. Okay. So the reasons are of various kinds. So, for example, if the essential type is inappropriate, if you put a floating point type where you don't have to, you may have a constant violation. For example, if you are trying to address an array using a floating. Or you may have a Boolean type that is unexpectedly interpreted as numeric. Okay. A character type interpreted as a numeric type as an implementation defined value. Let me remind you that plain char can have sign or can be signed or unsigned, and this is implementation defined. So similarly for the enumerated types, bitwise operator on negative operands may have an implementation defined value due to the representation of integer. Shift with the negative right-hand side is undefined behavior. Unary minus on an unsigned operand may have implementation defined sign. So these are selection of the reason why you shouldn't violate this rule. The rule applies to all the operands of arithmetic, logical, comparative, bitwise, shift, subscript, and increment-decrement operators, and to the first operand of the conditional operators, which, as we saw, must be a Boolean in all cases. Here is an example of violation. So Booleans are not numbers. You see the violation here? So we are using a Boolean to address an array. And so this is a violation. What is the solution? I don't know. Maybe the intention was this one. If the intention was to address the position with index 1 in case the x was true or 0 otherwise, this would be the MISRA compliant way to solve the violation. Okay, it's just an hypothesis, so I will not repeat too often enough the thing. I cannot tell you what is the solution, because the solution depends on the intention. Okay, maybe this was a typo. It was not x that was meant here. Okay, it was maybe y, which is a variable at file scope. Okay, so I cannot say what is the solution. If the intention was to address position 1 in case of x true or 0 in case of x false, this is the solution. Rule 10.2, expressions of essentially character type shall not be used inappropriately in addition and subtraction operator. And the reason is that essentially character type category represents pure character data. It does not represent numeric values. And in fact, the value is implementation defined. Okay, so in order to do an appropriate use of expressions that have essential character type as an operator of addition or subtraction, okay, the other operand must be essentially unsigned or signed. Okay, so as I said, the allowed expressions are useful for character conversion. So whenever you want to convert from, say, uppercase to lowercase, so if you are in ASCII, you have to add 32, I think. Converting between digits and their ordinal value. So in ASCII, again, in order to convert from the character 3 to its value, you should subtract 48, I think, to the ASCII code to obtain the value. And here's an example where we are violating this rule. So the violation is due to the fact that we are using a plain character to hold small integers. However, characters are not numbers. Okay, so this is a violation. The correct MISRA compliant solution. If you want small integers, say 8-bit, if your implementation supports 8-bit integers, then this is what you want. Okay, you use uint 8t, which probably will be a type def to unsigned char. This is the correct way of doing this. Rule 10.3, the value of an expression shall not be assigned to an object with a narrower essential type or of a different essential type category. And the reason is implicit conversions. And these implicit conversions are often not well understood by programmers. So what happens may be not what the programmer wants. And in addition, when the destination type is narrower or in different category, you can obtain unintended results. So you can lose the value, the sign, or precision. Precision, for example, when you assign a double to a float, maybe you preserve the sign, you preserve more or less the value, but you are not guaranteed to preserve precision, of course, as a float may have less bits than double. Okay, here is an example. We have two assignments. Small equals large, you see, tends to assign a 32-bit unsigned to a 16-bit unsigned, whereas real equals large uses assigns to a different type, essential type category. So the correct solution is not to leave this conversion implicit, assuming that they are wanted. So one possibility is, which must be used with great care, is to use explicit cast instead. And even though MISRA C doesn't prescribe that you also have comments, you should probably explain that, for example, in the first assignment, wrapping is either impossible or it's something that is wanted. It's consistent with the intention of the programmer. We'll come back to this subject later. Rule 10.4, both operands of an operator in which the usual arithmetic conversion are performed shall have the same essential type category. We have already seen why this is dangerous. So the implicit conversion may not be what one expects. So for example, we have seen this in the hidden enemy example. And again, when the destination type is in a different category, we can have an unintended result, losing the value, the sign, or the precision. Okay. Here is an example very similar to the hidden enemy example. It's a comparison where we compare a signed integer, 32 bits, to an unsigned, because size of is unsigned, the division of the two unsigned is unsigned. And as you have learned from the hidden enemy example, what will happen is that it is the signed that is converted to the unsigned, and this may give rise to very wrong results that are not what the programmer expected. So, possible solution is, assuming that IDX really has to be signed, is to introduce an explicit cast and then compare signed with signed, avoiding the implicit conversion, which would be the wrong one, and replacing it with the explicit conversion, which is what we want. Rule 10.5. The value of one expression shall not be cast to an inappropriate essential type. So a cast to an essentially Boolean type may result in an expected value that is not 0 or 1. So if this was the intention, a cast to an essentially enum type may result in a value outside the set of enumeration constants. So let's say you have an enumeration with A, B, C. So 0, 1, 2, you assign 7. It's outside the set of enumeration constants. So what will happen? A cast from an essentially Boolean type to any other type is unlikely to be meaningful. What does it mean to assign a Boolean to a float? No. Converting between floating point and character type is not meaningful at all, for example. Okay, so here we have an example where we are casting explicitly X, which is of signed type category 32 bits, to a bool. Oh, one might think, okay, but I know what happens here. No, it depends. So in C90, bool can be a type def for something. Okay, in the extreme case, bool can even be a type def for int. So this cast does nothing. And even in other situations where you are using different types to represent a Boolean in C90, this cast does not reduce the range of the result to 0, 1, which is what you would want. So this is a violation. The correct solution, if this was the intention, is to make the check explicit. In this case, the language ensures that to cont1, we will assign either 0 or 1, and not any other value. 10.6, the value of a composite expression shall not be assigned to an object with wider essential type. This might be striking to someone because the reasoning would be, what is the danger if I assign an object to a wider essential type? So it fits, so there should be no problem. And the problem is that there can be confusion about the type used to evaluate expression. Do you remember the imaginary friend example? This was exactly the case. Because John used a 64-bit variable to store the result of the addition, he made the wrong inference that the addition would be performed using 64-bit precision, which is not the case. Okay, so moreover, the type of an arithmetic operation depends on the size of int, and hence it's also implementation defined. And this can easily produce unexpected results. So here we have an example which is very similar to the example of the imaginary friend. Here, the programmer might have thought that since the result of the addition is passed to a function foo, which expects a 64-bit unsigned quantity, that the addition would be performed in 64 bits. No, the addition would be performed in 32 bits because both the quantities that have been added are 32-bit unsigned. Okay. So this is the violation of rule 10.6. And in order to solve this violation, if this was the intention, I mean, if the intention was that the addition had to be performed with 64 bits, you cast one or both the operands of plus to 64 bits. One is enough. You can also cast both if you want. But in this case, you will comply with the rule. Okay. So this is rule 10.6 is the first in a series of 3 rules that are all very similar, that are meant to prevent this kind of mistakes. So this one is has to do with assignments and passing to functions. And rule 10.7 is very similar. We go directly to the example. It's this rule applies when you are using composite expressions. So here the programmer might have thought that since the divisor is unsigned long, that also the addition would be performed using 64-bit for precision. In reality, this is not the case. This addition will be performed using 32 bits, independently from the fact that division will be implemented in 64 bits. Okay, so the solution is, again, if you want to make sure that the addition is performed in 64-bit unsigned arithmetic, cast one or both the operand to uint 64T. 10.8 is the same. It deals with the fact that the confusion of the programmer is due to the use of a cast outside. So here is the violation. The programmer might have thought that since there is a cast of the result of the addition to 64 bits, then the addition would be performed using 64-bit of precision. This is not the case. This addition will be performed using 32-bit unsigned arithmetic, and the result of the addition, possibly subject to wrapping, will be converted then to 64-bit. Okay? So again, the solution is the same as before. If you want to make sure that the addition is performed in 64-bit unsigned arithmetic, you cast one or both the operands to this time. Okay? So will these rules save your projects? Not necessarily, because these rules can all be complied with, so to speak, by adding explicit cast. And you know, everybody in the audience know at least one BPFH, the bastard programmer from hell. BPFH will add random explicit casts for the program, to the program, making completely fail the objective of this part of MISRA C. So here is an example, the examples we have started with, the hidden enemy example and the imaginary friend example. Here, BPFH adds the wrong cast, the wrong explicit cast here. It adds a wrong explicit cast here. So it obtains the objective of silencing all the violation of the MISRA C 2012 rules in section 10. The program is, the two programs are as buggy as before, but this time they are clean. So you see, this is very, very dangerous. Okay. However, will this rule save your project? The positive side is yes, with proper compliance and some discipline. For example, we recommend adopting, in addition to MISRA C 2012, several rules of BAR C 2018, and in particular Directive 1.6.a, which says each cast shall feature an associated comment describing how the code ensures proper behavior across the range of possible values on the right-hand side. Okay, and Eclair features the best support for BAR C 2018 available on the market, and in particular for that directive, the tool will tell you will signal to you all the explicit cast in which there may be a loss of sign, of value, or of precision that have not a comment explaining them. Okay, the tool will be silent for casts that are safe, so that do not give rise to loss of value, sign, or precision. But for the others, it will prescribe the presence of a configurable comment that can then easily be instructed from the source, so that you can check if you have one or more BPFH in your team, which is a bad thing. Conclusion. So we introduced the MISRA C 2012 essential type model, and along with the MISRA C rules that are based on such models. So we have explained that these rules are there in order to avoid some implementation defined behaviors, avoid mixing data that have a different nature, improve code readability, avoid subtleties, that have to do with integer promotion and user arithmetic conversion and improve code portability. There are, as usual, important messages to take home. So, despite the fact that in the polls I have chosen the most difficult question I could think of, and almost all the examples were chosen for not well-behaved expressions, learning MISRA C is easier than learning the full C standard. Another important message to take home is that it is technically possible to defeat the whole point of MISRA compliance if you really want to do it. So, for example, adding random explicit casts can leave all the bugs there, can even introduce more bugs and result into MISRA compliance. And as usual, good tooling and training are key to the successful adoption of MISRA C. So now I'm ready for questions, if there are any. And before we move to the question, let me draw your attention to the fact that this is last webinar before a break that we will have in August. However, in September, we have a very rich webinar program. So we will have, on September 3rd, we'll start with a webinar that is especially recommended for program and project managers, so MISRA compliance and legacy third-party code. Then we have a joint webinar with SolidSense, which is a leading supplier of qualification suites for C, C++ compilers, and C++ libraries. So this webinar will be on language subsetting and compiler qualification in the development of software for safety critical systems. Then we will have on September 22nd another BUGSENG webinar, Understanding Implementation Defined Behavior in C and C++. Very recommended this. There will be some special effects in this webinar, so I recommend you to register. And on September 29th, we will have a joint webinar with an American company, A-Fusion, which is probably the largest consultancy company for the development of safety critical systems. They are particularly active in aviation, but also in other industry sectors. So this webinar will be MISRA C, the power of C without the pitfalls. So you can register to all webinars on our website at the address provided here. Now, questions.
Okay, thank you, Roberto. Let's go with the first one. Obviously, the essential type system is hard to understand. Does it really help avoid mistakes? Though I have to admit that tools can check it quite well.
Yeah, so it's not so difficult to understand when you start using it, and especially when you use a good tool. A good tool will tell you exactly how the essential type category and size have been determined. So maybe it's my fault. I have chosen the most difficult questions for the polls, but I can assure you that if you learn to work with discipline, so for example, if you never mix signed with unsigned, if you don't mix plain characters in unwanted ways with other data types, then immediately seeing what is the essential type category is 90% of the time trivial, and for the rest, if you have a good tool, it will guide you exactly at understanding. And so this is one of the reasons why we have spent so much energies in the quality of our reports. So because with this, the skills of the team increase over time. So in a sense, the tool teach the team about things concerning the C standard, and also in this case the essential type system. And the combination with the bar C rule that I have explained is also very, very, very useful. Very useful. And if your programmers stick to this rule of always adding a sensible comment to explicit casts, then this will definitely increase the readability of your code, and in the end, all will be very clear.
Okay, thank you, Roberto. The person who asked the question specified, thank you. My question resulted from the poll, so that was the reason why he asked.
Okay.
All right, so next question. Why is signed converted into unsigned and not the other way around in binary addition?
Well, to understand this, you should probably go to the YouTube channel and look at the recording of the previous webinar. So the rules of the language are done this way. The short answer could be why not? Because neither is safe in all cases. Okay, so signed converted to unsigned is dangerous in case you convert a negative value. Unsigned converted to signed is dangerous because you can end up in an overflow as well. So if you look at the recording of previous webinar, you will see that the people behind the C standard have actually been quite careful when defining the usual arithmetic conversion. I think that in the end, they favored converting signed to unsigned because of the well-definedness of modulo arithmetics that is associated to unsigned integers.
Okay. Essential type system is usable to check abuses of nominal typing. For example, I have types for seconds and type for meters, and I don't want that the two are mixed accidentally.
Okay. So this is a good question. The essential type system could help you to flag some of these things if the different quantities you are mixing have different and incompatible essential types. However, I think that the concept can be quite easily extended in a tool. This is maybe an idea for an extra service that Eclair may provide. So to support the definition of supplementary types with type rules, so that the tool can tell you whether you are mixing, I don't know, you are adding meters to kilometers represented as integer, or meters to seconds.
Okay, thank you, Roberto. And thank you again, everybody, for joining us today. Of course, if more questions come to mind, you can always drop us an email at info@bugseng.com. As anticipated, please check out our YouTube channel later on for the recording of today's webinar. Our YouTube channel is in general a good informative spot, as Roberto said. We covered many topics over time, and we also upload useful demos of our static analysis tool Eclair, which of course we invite you to try. Okay, so August is upon us. So as Roberto said before, we will take a little break and come back on September 3rd with MISRA Compliance and Legacy third-party code. You will receive the registration link in the post-webinar mailing as well. I posted it before in the Q&A section if you want to copy and paste it somewhere. All right, so that's it from us today. Thanks again for attending. We wish you all an exciting and hopefully relaxing summer break, and we look forward to hear from all of you very, very soon. Goodbye, everybody.
Bye-bye.